Hello friends, let us today in this very lecture, we are going to begin with solving and understanding of certain questions which are basically here presented before you to test your knowledge on the topic relations and functions. These JEE advanced pattern questions are going to basically help us brush our entire concepts and polish our understanding about this chapter. So let's proceed with them. The first question here presented to test our knowledge basically is asking us to find the domain of a certain function. If you carefully observe, this function is obtained by taking the square root, number 1, of sine inverse 2x, number 2. Why am I saying number 1, number 2? Because there are two different types of functions involved to make the function f. I know when is my square root function defined. Well, if I proceed and start with the solution and take, say, under root x as my function, we all know that the domain of under root x is nothing but 0, infinity. In fact, the range also is 0, infinity. And in fact, the graph goes something like this. This is my function fx equals under root x. That means when I am saying that 0, infinity, 0 included, is the domain of under root x, I mean only real numbers which are sitting inside this interval 0, infinity are the valid inputs for under root x. No real number which is not non-negative can enter as input inside the function root x. That means for under root, this inside expression to be defined and go in the real number set, this inside expression should definitely belong to 0, infinity. That is, what is the inside expression? It is sine inverse 2x plus pi by 6. This should belong to 0, infinity for f to belong to R, or I should say fx to belong to R. Because I am interested in those values of small x coming from the collection of reals for which fx belongs to the collection of reals. And that can only happen when under root of this expression is a valid expression. And this is valid only when the input of the root function is belonging to 0, infinity. Which means sine inverse 2x plus pi by 6 is greater than or equal to 0, which now means that sine inverse 2x is greater than equal to minus pi by 6. Let me mark this as equation number 1. That means sine inverse 2x is greater than equal to pi by 6. This should hold for under root of this expression to come out to be real. Now you have to understand, I am over here talking about the inverse of sine function. How did this come into picture? If you remember the sine graph, this is the behavior of the sine graph. And if I am saying this is my sine x function, obviously you can see it is not 1, 1. Yes, the range is what? The range is the closed interval minus 1, 1 because it is only attaining values from minus 1 to 1. Look at the height of the graph. Height of the graph above the x-axis is maximum 1 and below the x-axis the height is maximum 1. Below the x-axis the number it attains is minus 1, above the x-axis the number it attains is 1. and that is why the range of sine function is minus 1, 1. So I can say that sine x from r to minus 1, 1, which is range of the sine function, is an onto function, because over here codomain is equal to the range. But what about the domain? I want my function to be 1, 1 also for it to be invertible, and that can be done provided my function sine is 1, 1 on the domain R. But by the horizontal line test, you can very well see if you are going to make a horizontal line, it is going to intersect the graph at more than one point. That means over the real line sine function is not 1, 1. That is why we are going to restrict the domain to minus pi by 2 to pi by 2. And corresponding to this interval minus pi by 2, pi by 2, the function will be attaining all values from minus 1, 1, and only this yellow portion graph will be drawn. And if you just consider this graph, which is drawn corresponding to minus pi by 2, pi by 2, it is an increasing functions graph, and therefore if you are going to draw any horizontal line, it will intersect this yellow portion only once. That is why I say that sine x from minus pi by 2, pi by 2 to minus 1, 1 is both 1, 1 and onto. That means over this domain, every distinct member is going to distinct member. That means distinct members sitting in this domain are mapped to distinct members sitting in this codomain under the function sine. And with this codomain, because it is equal to the range, the function is onto also. And that is why sine has become 1, 1 and onto with this domain and this codomain, which implies sine x from minus pi by 2, pi by 2 to minus 1, 1 is invertible. Because it is invertible, this implies there exists its inverse. The output set for sine becomes the input set for sine inverse, and the input set for sine becomes the output set of sine inverse. And we know the definition of F inverse happens to be this function applied to the input x comes out to be y only and only when sine y is equal to x. We have done the concept of inverse of a function. I am just applying that same concept over here. And this means whichever x you put over here coming from minus 1, 1, sine inverse x is going to go inside minus pi by 2, pi by 2. That is, for all x belonging to minus 1, 1, sine inverse x belongs to minus pi by 2, pi by 2. Right? Over here in the question we have sine inverse 2x. Just make the argument instead of x equal to 2x. The argument still remains the same. This entire concept that I have taught you is for your understanding, because I am using this completely in this question. And therefore, we have understood that sine inverse of this argument is always greater than equal to minus 2 and less than, greater than equal to minus pi by 2 and less than equal to pi by 2. From here I had sine inverse 2x is greater than equal to minus pi by 6. By the very meaning of sine inverse, it is always coming out to be less than equal to pi by 2. Right? And that means if I mark this as equation number 2, from 1 and 2, what is it that we have obtained? 1 says sine inverse 2x is greater than or equal to pi by 6, and 2 says something about it being less than or equal to. Let's write that down once again and then begin solving it. So I have sine inverse 2x is greater than or equal to minus pi by 6 and less than or equal to pi by 2. That is what I have used over here. Now is the time to solve something. Well, if you carefully observe, this is my pi by 6, this is my pi by 2. Pi by 6 is 30, pi by 2 is 90. Similarly, here this is my minus pi by 6 and this is my minus pi by 2. So, because right now I am only concerned with sine inverse of something being between minus pi by 6 to pi by 2, the definition of inverse says whenever x belongs to minus 1, 1, in that case sine inverse x equals y implies sine y equals x, provided x is coming from this interval and y is coming from this interval. That means sine inverse x equals y can be written as sine y equals x, provided we are working in this domain and this range, which is true over here because minus pi by 6 to pi by 2 is very much in the interval minus pi by 2, pi by 2. And that is why by the definition I can write sine of, this can happen only when sine of minus pi by 6 is less than or equal to 2x is less than or equal to sine of pi by 2. And this means what? Well, sine of minus theta is minus sine theta. So we are left with minus sine pi by 6 is less than or equal to 2x is less than or equal to sine of pi by 2. Sine of 30 degrees is 1 by 2. So this happens to be minus 1 by 2 is less than or equal to 2x is less than or equal to, well, sine 90 is 1. And this gives you minus 1 by 4. Just bring this to the side, is less than or equal to x is less than or equal to 1 upon 2. And this can be written as x belongs to minus 1 by 4 comma 1 by 2 closed interval. And that means it is these values of x which make this expression of f bring out real values. That is why only these x's are valid to get entry inside the machine f, because only corresponding to these x's the machine is delivering real values, and so this happens to be my domain of f. Let's see which option helps us to get this as the answer. Minus 1 by 4 comma 1 by 2, the very first option happens to be the correct one because it tallies with our solution, and therefore A is my correct answer. B definitely is wrong, C is wrong, and D is again wrong. This is how we proceed with the questions involving domain of a function. Understand carefully, here I have tried to explain you the sine inverse existence concept also. We have already done the inverse of a function concept, and this is just application of that concept to a specific function, which is sine in this case. So let us, without any further ado, start understanding what is the next question. Well, question number 2 in this case is trying to basically tell us something else about functions. It is saying, suppose f is defined by x minus 4, g is defined by this particular detailed format, wherein this lambda value that you can see means what? It is saying that g function at the point minus 4 is attaining the value lambda, and G at points not equal to minus 4 is attaining a value given by this expression. And then when f and g are given in this way, it is saying find lambda such that fx is equal to gx for all x if this is true. And that means that is what I am supposed to find. So if fx is equal to gx for every x, what do you think is lambda going to be, which is going to make these two functions equal to each other? So let's start with it. Fx is equal to gx is what is given to us. That is what I want basically, that fx should be equal to gx for all x in R. But this is equal provided corresponding to every x sitting here as input, the output produced by f and g is the same. And therefore, if f and g are equal for every x in the real line, definitely corresponding to x equals minus 4 also they will be equal. That means if f is equal to g for every x, this implies for x equal to minus 4, also f of minus 4 is equal to g of minus 4. Why not? If they are equal for every x, definitely they are equal for minus 4 also. But f of minus 4 is going to be found by the definition of f, which is x minus 4. So f of minus 4 happens to be minus 4 minus 4. Whereas g of minus 4 will not come from this expression. In fact, if you try and incorporate minus 4 over here, the denominator will give you 0 and this will be an undefined term. That is why corresponding to minus 4, g has been provided some other value. I don't know what that value is. Let us find out therefore. And because we need g of minus 4, right now it is unknown to us. So let me just write that unknown quantity only, which is standing for g of minus 4. So this brings to be lambda equal to minus 8. That means it is for lambda equal to minus 8 such that fx is equal to gx for all x. When lambda will be equal to minus 8, then in that case fx will be equal to gx for every x. Just replace in place of lambda, you replace minus 8, even the different looking functions f and g. Just understand, f is just this simple expression x minus 4, whereas g is this expression which is x square minus 16 upon x plus 4 for these values of x and minus 8 for minus 4. This branch function is equal to this simple function for lambda equals minus 8. That is what is the answer. Two completely differently looking functions can also be equal functions. They will deliver exact same output corresponding to every input coming from reals, only when in place of lambda you put minus 8. And therefore, the correct answer is given by point number B, which is minus 8. Pretty simple question. Yet, you have to understand that intuitively at the first go it feels that this need not be true, because they are completely two different looking functions. One is a simple polynomial, other is a difficult branch function, but yet they are equal for a certain value lambda. Question number 3 now is trying to tell us about relations. Let R be a relation on the collection of all natural numbers defined by this expression. It is saying that in the ordered pairs, as the first component will sit this type of members and as the second component will sit this type of members, where x is natural number less than equal to 5. That is what is given to you. So which of the following statements is true? The following statements are basically among the first statement is trying to give you the entire expansive form of the relation R. In order to tally whether this R is correct or not, we will have to actually find the relation. So let's find it. We are given that R is a relation on the set of all naturals. This means my R is a subset of n cross n. R is a subset of n cross n such that inside the relation R sit those ordered pairs belonging to n cross n such that the first should look like 1 plus x and the second component should look like 1 plus x square. So this, if I mark it as x1, y1, then such ordered pairs are sitting inside R such that x1 looks like 1 plus x and y1 looks like 1 plus x square, such that this x is coming from where? This x is coming from a set A where A is 1, 2, 3, 4 and 5. That is what is the meaning of the question. Inside the relation R sit such ordered pairs whose first component looks like this, second component looks like this, and in these two components the place of x, the role of x is being played by these members. Because here it is given x is a natural number less than or equal to 5, that means x ranges from 1 to 5. That is what is my set A. Now if I wish to find this relation, I basically wish to find a subset of n cross n, which basically stands as a relation from n to n, relating members of n to members of n in this format. So let's start with the first natural number. If x is equal to 1, this implies, or I should say x1 is equal to 1, because that is what I am portraying my first components as, because x symbol is reserved for these 5 members. So if x1 is 1, which is the first natural number, then 1 plus x or 1 plus x1 will happen to be 1 plus 1, that is 2, and 1 plus x1 square will happen to be 1 plus 1, that is 2 again, giving you 2, 2 ordered pair belonging in the set R. Now if I begin with x1 equals 2, this would imply 1 plus x1 is equal to 3 and 1 plus x1 square will be 1 plus x1 square is 4, which is 5, delivering the information that 3, 5 also belongs to R, right? Because inside R are sitting such ordered pairs where the first component is formed with the help of 1 plus x type of things, where x is coming from 1, 2, 3, 4, 5. Now, if I take x1 equals 3, you get 1 plus x1 equals 1 plus 3, that is 4, and 1 plus x1 square happens to be 1 plus 3 square, which is 1 plus 9, making it 10, which implies 4, 10 belongs to R. Moving to the fourth natural number, x1 equals 5. Oh, x1 equals 4. In this case, your 1 plus x1 is what? 1 plus 4, that is 5. And your 1 plus x1 square happens to be 1 plus 16, that is 17, pushing this ordered pair 5, 17 inside R. Next natural number is 5, which implies 1 plus x1 gives you 6 and 1 plus x1 square gives you what? 1 plus 25, that is 26, pushing 6 comma 26 inside the relation R. Up till here, we have obtained 1 plus x for x equals 5. After that, if we start discussing, I will be moving to x1 equals 6, giving me 1 plus x1, which is 1 plus 6, which is 7. But the relation says the first component should look like 1 plus x, where x is coming from these 5 members. That means this x can take only these 5 values. It cannot take 6 or 7 or 8 or any one beyond 5. And that means our process of obtaining ordered pairs sitting inside R stops at x1 equals 5. We cannot take x1 equals 6. Or we cannot go beyond x1 equals 5, and that is why your R gets completed as the collection of ordered pairs 2, 2, 3, 5, 4, 10, 5, 17, and 6, 26. That is what it comes out to be. This R is the set of those ordered pairs wherein the first component looks like 1 plus x and second component looks like 1 plus x square, where x ranges from 1 to 5. Obviously, the domain of this R is the collection or the set of all the first components sitting in the ordered pairs, which is 2, 3, 4, 5 and 6. And the range of the same relation R, if I wish to find, happens to be the collection or the set of all the second components sitting in the ordered pairs, which are 2, 5, 10, 17 and 26. This is what it turns out to be. Now is the time to go and verify whether the options basically satisfy these solutions or not. The first option says that corresponding to this rule, the R which comes out is 2, 2, yes, it was a member, 3, 5, yes, definitely, 4, 10, was it coming out? 5, 17, 6, 25. Well, let's go and check. We had 4, 10 definitely coming out with us, and therefore 4, 10 is sitting in the relation. 5, 17 is also sitting in the relation, and 6, 26 is sitting in the relation. But over here, 4, 10, 5, 17, no problem. 6, 25 is the problem. It does not sit inside the actual relation R, and that is why A is not the correct option. My relation is not equal to this. It is equal to 6, 26 at this position. But domain of R is yes, 2, 3, 4, 5 and 6 definitely. So B is correct. Range of R is 2, 5, 10, 17, 26. Yes, it is correct. And option number D, which says both B and C are true, is also correct because yes, both B and C are true. That is how just by one digit's difference, we have eradicated A from being the correct option. That is how silly sometimes students commit mistakes. They do not watch how trivial solutions can differ from each other, and they end up getting the wrong solution marked. Next question, which is in the league waiting for our attention, let's see is what? Well, the next question talks about range of a function. So what is it trying to say? Why don't you give it a reading? It is saying range of a specific function given in this format is what? That means I have to find fx or y equals what? Well, I told you the algorithm to find the range of any function. That is what we are going to use over here to obtain the solution of this question. The first step in the algorithm was equate y equals fx. That means y is equal to x square plus x plus 2 whole upon x square plus x plus 1. Now very well you can see that somewhere above also x square plus x plus 1 can be made. That is, I can write it as x square plus x plus 1 plus 1. Right? Whole upon x square plus x plus 1. I have just broken 2 as 1 plus 1. And this expression then can be written as x square plus x plus 1 whole upon x square plus x plus 1 plus 1 upon x square plus x plus 1. And now this definitely gets cancelled and you get 1 plus 1 upon x square plus x plus 1. Now carefully observe, this is my y as the output and it is saying or it is coming out to be equal to this expression. Now here 1 is sitting, in the denominator I have x square plus x plus 1, the denominator is always strictly greater than 0 because even if you put 0 in place of x, always you are going to get a non-zero answer in place of the denominator. That is what you are going to get, and that because x square is always going to be non-negative, you are going to get this expression always to be non-zero. And 1 obviously sitting in the numerator makes it non-zero. Therefore, this entire expression when 1 is added to it always gives you greater than 1 expression. That means y, which is equal to 1 plus 1 upon x square plus x plus 1, is always going to be greater than 1. This is a very important point of observation, that the output which you are going to get is always going to be greater than 1 strictly. Now if I proceed with solving the expression which was given to me, I was given y is equal to x square plus x plus 2 whole upon x square plus x plus 1. Just cross multiply and solve the expressions. You get yx square plus y into x plus y is equal to x square plus x plus 2. And just bring the like terms aside, you get x square y minus 1 plus x y minus 1 plus y minus 2 equals 0. Now if you carefully see, this y minus 1, y minus 1, y minus 2, what are these? Can I say if I take y minus 1 equals a, this y minus 1 as b and y minus 2 as c, this is nothing but the expression ax square plus bx plus c equals 0. This quadratic equation will have roots, only real roots, and that is because x is belonging to the collection of all reals. A quadratic equation has real roots if and only if its discriminant is non-negative. That means since x belongs to R, implies the discriminant of this particular quadratic equation is greater than equal to 0. And the discriminant is given by b square minus 4ac, where b is coefficient of x, a is coefficient of x square, c is the constant term. And therefore, if I have this expression to be equal to 0, where x is coming from real numbers, this implies the discriminant of this quadratic equation is non-negative, which means b square. So take y minus 1 whole square minus 4 into a is again y minus 1, into c, which is y minus 2. This is non-negative. Let's solve it out. You get y minus 1 whole square minus 4 into y minus 1 y minus 2 is greater than equal to 0, which I can take out my y minus 1 common and get inside the bracket y minus 1 minus 4 times y minus 2. This implies you have inside this bracket y minus 1 minus 4y plus 8. That is what you have. This means you have y minus 1, inside it you have y minus 4y, which makes it minus 3y, and 8 minus 1, which makes it 7. And this expression, basically if you consider the individual factors, is going to give you two real numbers. If you equate y minus 1 to 0, it will give you 1. If you equate this expression to 0, you will get 7 upon 3. Now, we have to find those values of y which when substituted in this expression give you non-negative answers. Suppose I pick up negative reals, that is these. When I pick up negative reals, I am going to get negative answers. That means the output will not be non-negative. This is going to deliver me negative answers, minus sign. If I move from 0 to 1, from 0 to 1 means members which are less than 1 is again going to deliver to me negative results. If I move from 1 to 7 by 3, yes, from 1 to 7 by 3, the digits in place of this y will be greater than 1. So this expression will be positive or non-negative. And over here, if I again substitute y, which is greater than 1, less than 7 by 3, again this will be non-negative, giving the product to be non-negative. So this is the correct range. In fact, if I move beyond 7 by 3, I will be increasing numbers by greater than 7 by 3, and then this will be creating a problem. It will make the expression negative. So the only values of y which when substituted in this expression deliver non-negative results is this range. That is, for this expression to be non-negative, y should come from 1 to 7 by 3. But mind it, we had understood that our y is strictly greater than 1. That means it cannot be equal to 1. So here in this closed interval, I have included 1, but I will have to actually exclude this 1 because y cannot be 1. This implies y is equal to 1 excluded, 7 by 3 included, this interval, and y stands for the output. This is what is my range of the function f. We have just followed the algorithm and found out our range, which is 1 open, 7 by 3 closed interval. Let's see if we have that in the options. The first option doesn't deliver that, it's wrong. The second option again doesn't deliver that, it's wrong. The third option is yes, it's correct, and D therefore is wrong. This is how, by just using the algorithm, we have successfully found that what actually happens to be the range of the function f. Just step by step apply the algorithm and come up with this solution. We are going to start with question number 5 in a bit of a time. Till then, why don't you practice this once again and understand what concept had I used here to basically reach to the range of this function. Having understood how have I, using the algorithm, found successfully the range of this function, let us now begin understanding what is the demand of the fifth question for us. It is trying to say that let A be the set of two positive integers. I don't know which are those two positive integers. A is just the set of two positive integers. Let f be a function from a to z plus, which is standing for the set of positive integers, or you can say natural numbers. And this f is defined by the rule that f of n, when f is applied to positive integers sitting inside a, the output is that integer which is the highest prime factor of the input. The output is that particular integer which is the highest prime factor of the input integer. First of all, highest, then prime. Also, one more fact is given to us that range of f is singleton 3. Then the question starts. So, before that, let us understand how the function is behaving. I am given a is the set of two positive integers. I don't know what those two integers are. So, let me say let a be the set of two positive integers n and m, where n and m are any two positive integers. And also I am given f is a map from this a to z positive such that f, when applied to any input coming from set A, delivers the highest prime factor of n, or of x in this case, because x I am using as input. Now that I have this, let's see one more fact which is given to us. Because this function, yes, definitely is from set A to n, because z plus is nothing but n. Inside A, I just have two members n and m. Inside n, I have so many natural numbers, 1, 2, 3, 4 and so on. But the range of the function, which is the set of obtained outputs corresponding to all the inputs, is given to be just singleton 3. That means when this small n enters as input inside f, the function f delivers the output as 3. And when the next positive integer m, when this enters as input inside f, the output delivered is again 3. That means f of n is 3 and f of m is also 3. But f of x is 3 implies 3 is the highest prime factor of n. So, from these two, I can say by definition that 3 is the highest prime factor of n and of m. So, if n and m are distinct from one another sitting inside set A, then 3 is the highest prime factor of n and m implies, if I take this as case 1, I can have n to be equal to 3 and m to be equal to 6. Because 3 is the highest prime factor of 3 and 3 is the highest prime factor of 6, and that is why I am taking n equals 3 and m equals 6. Why don't you try and find out some more values of n and m which satisfy this particular relation, and then we will proceed with the solution. So could you guys find out what are those possible values of n and m for which 3 is the highest prime factor of n also and highest prime factor of m also? Well, if I take n equals 3 and m equals 6, then definitely 3 is the highest prime factor of 3 and 3 is the highest prime factor of 6, which implies in this case 3 in place of n and 3 which is the output, and 6 in place of m and 3 which is the output. Both these ordered pairs belong to the function f, which would imply that my set A happens to be n comma m, which is 3 comma 6. Suppose I take case 2 in which I take n equals 6 and m equals 9. In this case also I can get f of n equals 3 and f of m equals 3. Because 3 is the highest prime factor of 6 if I take n equals 6, and 3 is the highest prime factor of 9 if I take m equals 9. And that is why I can take n equals 6 and m equals 9, giving me that A is equal to 6 comma 9. Right? In fact, you could have even taken n to be equal to 3 and m to be equal to 9. Because 3 is the highest prime factor of 3 and 9, making A to be equal to 3 comma 9. That is why I can have A to be this also, A to be this also, and A to be this also. In fact, this list can go on. That means there are many, very many A's which I can form, which if kept as the domain of this F are going to give this kind of a behavior. For A as 3 comma 6, for example, I am going to get f of n equals 3, f of m equals 3. That means f of 3 equals 3, f of 6 equals 3, giving me the same arrow diagram. If I will take A to be equal to 3 comma 9, again same arrow diagram. If I am going to take A to be equal to say 6 comma 9, again same arrow diagram. That means with the help of many A's, I am getting the same function f with this definition. And then the question says, which of the following options are true if statement 1 is A is uniquely determined and statement 2 is A is not uniquely determined? Then option number 1 says statement 1 is true. Is it true? Is my A uniquely determined? Not at all. There are many A's which when put in place of domain of F are giving you this result. And so A is not true. Statement 1 is not true, and that is why A is false. B option if I take, it is statement 1 is false. Yes, it is false, and so B is true. Statement 2 is true. That is, A is not uniquely determined. Yes, it's true, because yes, A is not uniquely determined. A can take a lot of forms. And D says both are true. This is also true and this is also true. Of course not. Not at all. If statement 1 is true, statement 2 cannot be true. If statement 2 is true, statement 1 cannot be true. In this case, statement 2 is true and statement 1 is false. That's how we have dealt with this question concerning functions. Because the same behavior of functions was being exposed by different sets A That is why using that particular idea we have obtained the correct solution of this question. Let's see what happens to be the next question in the league. Question number 6 is what's coming up next. What is said by this question? Why don't you take a look at it? Question number 6 is trying to say, let a relation R1 on the set R of all real numbers be defined as A, B belongs to R1 if and only if 1 plus AB is greater than 0 for all AB in R. Over here, this R is standing for the collection of all reals. That is why R1 is the name given to the relation instead of R. So mind it, A, B belongs to R means A and B are real values. Then, which of the following is false? It is saying A is related to A under the relation R1 for all A in the collection of all reals. Then it is saying there is some real number which is not related to itself under the relation R1. Then it is saying A is related to B under the relation R1 implies B is related to A under the relation R1 for all AB in the collection of all reals. And it is also saying there exists some A and some B inside R such that AB is related or A is related to B under R1 but B is not related to A under R1. Let's try and find out if this is true or this is true and this is true or this is true. First of all, if I have to show A is related to A under the relation R1 for every A in the collection of all reals, I basically will have to show that 1 plus A into A, that is 1 plus A square is greater than 0 for all A in R. Now always we know that A square is a non-negative term. So if you are going to add 1 to a non-negative term, you are always going to get a strictly positive term. And therefore, 1 plus A square is greater than 0 for all A in R, delivering that A, A belongs to R1 for all A in R. That means every real number is related to itself under this very relation R1. There is no real number which is not related to itself under R1, and that is why if option number B said that there is a real number which is not related to itself, this is wrong because each member of R is related to itself under R1. If I wish to talk about symmetricity, because this basically is talking about reflexivity and so R1 is a reflexive relation. Let's check if R1 is symmetric or not. So, let A, B belong to R1. That is, A is related to B under the relation R1. Then, I have to show B is related to A under the relation R1. That means I have to show 1 plus B into A is greater than 0. Now because it is given A is related to B under the relation R1, this implies 1 plus A into B is greater than 0. If 1 plus A into B is greater than 0 and A and B are real numbers, we know that A into B is same as B into A. And so this implies 1 plus B into A is greater than 0. One in the same thing. And that is what was wanted to show that B is related to A under R1. And so, since 1 plus A into B is same as 1 plus B into A which is greater than 0, thus this implies B is related to A under the relation R1. And because there is nothing special about A and B over here, they are arbitrary real numbers chosen. That is why if A is related to B under the relation R1, then B is related to A under the same relation is true for every real number A and B. And that means there does not exist any pair of reals such that A comma B belong to R1 but B comma A does not belong to R1, because this relation is very much symmetric. Thus, this question is basically testing our knowledge about reflexivity and symmetricity. If we have that concept clear with us, this question was a cakewalk and nothing else, and we were able to sail through this question having the correct options right before us. Without any further ado, let's try and see what is the demand of the 7th question in this league. It says that fx is given to be this expression, then the domain of f is what? Well, here again I am trying to find the domain of the function. That means what are the valid inputs which can be inserted inside the machine f. By valid inputs I mean what are the values of x for which fx is going to deliver real values as output. If there is any x corresponding to which fx is not delivering real value as output, don't put that x inside the input set of f. And that means corresponding to this machine defined like this, I have to find out what are the real numbers, the real values for which this machine is delivering real output. Now, if you observe, this is made up of logarithmic function, sine function, square root function. So many functions. Let's begin step by step. Pick up the innermost function. Well, here I am talking about log of a certain thing. You know that if I talk about log, then the definition says that log x to the base a has the domain 0, infinity, and the range is equal to the codomain, which is the collection of all reals. Always this happens. That means log x to the base a is defined. By defined I mean that log x to the base a belongs to R. That means it is not an undefined term but a defined real value only for x coming from 0, infinity. Because inside the domain sit only those members which are belonging to 0, infinity, which means only for these real numbers log x is delivering real values. So, for log of this expression, which is under root 4 minus x square upon 1 minus x, for this expression to be defined, first of all, and why do I need this to be defined? Because sine can act upon only real values. Until and unless this expression complete from log till the end is not real number, sine cannot act upon it. So for sine to act upon it, this should be real. And for this to be real, I want that under root 4 minus x square upon 1 minus x should be belonging to 0, infinity, or it should be greater than 0. So, for sine to act upon it, this expression should be real. For this expression to be real, this expression should be greater than 0. And for this expression to be greater than 0, what is it that I want? I want either both the numerator and denominator should have a minus sign, or both numerator and denominator should have a plus sign. Only then can I get greater than 0 expression. But root of anything is never negative. That means the numerator is always non-negative. So there is always a plus sign over here. That means for this expression to be positive, even the denominator should possess a plus sign, that is 1 minus x should always be greater than 0. First of all, this cannot be 0. Why it cannot be 0? Because if this becomes 0, then this entire rational expression will become undefined. That is why I don't want 1 minus x to be 0. I want it to be strictly greater than 0. This is not allowed to be less than 0 in fact, because numerator is always positive or non-negative. But denominator, if happens to be negative, this entire expression will be negative, which I don't want. Now, as I said, I have kept 1 minus x strictly greater than 0 and 1 minus x is not equal to 0, which means x is not allowed to be 1. But what if inside the under root expression I get a 0? Well, what I am trying to say is, I am just trying to use the concept that root x is defined from 0 comma infinity to 0 comma infinity. That means for x belonging to 0 comma infinity, root x always belongs to 0 comma infinity. Right? Whenever you put input from this interval, you get the output sitting inside that interval. And in fact, root x is an expression which goes inside the real line only if x comes from the input set of root x, which is 0 comma infinity. So for under root 4 minus x squared to be actually a real number, first of all, I need that this 4 minus x squared should be belonging to 0 comma infinity, or it should be greater than equal to 0. But if 4 minus x squared happens to be 0, then under root 4 minus x square will be under root 0, which is 0, in which case you will have numerator equal to 0, the entire expression will turn to be 0, and definitely it is not greater than 0. And so I cannot take 4 minus x square to be equal to 0, and this implies 4 minus x square will have to be strictly greater than 0. Or I mean by this, x square has to be strictly less than 4. If you remember the graph of x square, this is what it was. It basically said, if this is my minus 2 and this is my 2, then corresponding to minus 2 I obtained a 4, and corresponding to 2 again I obtained a 4. That is what was the behavior being possessed by the square function. If I want my x square to be strictly less than 4, that means I want my x to be between minus 2 and 2. So for x square to be strictly less than 4, my x should be strictly greater than minus 2 and strictly less than 2. But I also have certain other rules, that x cannot be equal to 1. That is what I know, and also I know that 1 minus x is strictly greater than 0, which implies x is strictly less than 1. That means I have this rule and this rule left to be imposed. So not just x is greater than minus 2 less than 2, but it is also true that x is less than 1 and x is not equal to 1. So if on the real line I try and plot these x's, I get that my x is less than 1, which means towards here. I also get x is not equal to 1, and x is ranging from minus 2 2, 2. Just understand what is the common portion. It is what? From minus 2 to 1, both excluded, is what is my common portion, and this implies x should belong to open minus 2, open 1 for this expression completely to be valid. For denominator also to be 0, non-zero and greater than 0, and numerator also to be greater than 0. Only then will this expression will be greater than 0, and only then will log be applied to it, and only then will sign be applied to this. So sign will be applied to this expression only when this expression is real. This expression is real only when this expression satisfies the condition that x belongs to minus 2 comma 1 open interval. And so only for these x's, this entire function is going to deliver real values, and therefore minus 2 comma 1 given by option number B is the correct answer. That is what is the logic which is used behind solving this question. Until and unless your knowledge about domain and range of the functions is not thorough, you will be having a tough time dealing with such questions, because these questions are only and only involving the concepts of domain and range of certain functions. You will not be given single valued functions like just sign or just log. Just like this in a mixed manner, all these functions will be given to you and you will be asked to find their domains. We are going to begin with the next question. Let me present that before you right after this while. After having dealt with the 7th question, let's start dealing with the 8th question, which is saying let f from R to R be such that fx is 2 to the power x. Very familiar function, the exponential function, where this a, which is playing the role by 2 over here, is greater than 1. Then which of the statements is true? Well, I know that what happens when I have fx equals a to the power x with a being greater than 1? Well, fx equals a to the power x, a greater than 1 has what as the domain? The domain is the collection of all reals, and the codomain is what? Again, the collection of all reals. But I know that the range of this function a to the power x is 0 comma infinity. We know that the graph of a to the power x goes like this for a greater than 1. That means it only covers real values which are greater than 0. That's why range is equal to 0 comma infinity open interval. And so the question is saying, is the range of 2 to the power x? So if a is greater than 1, for any a greater than 1, this is the graph. So for a equal to 2 also, this is the graph and this is the range. And thus this implies range of 2 to the power x is also 0 comma infinity, which is nothing but the set of all positive reals denoted by R plus, and therefore yes, A is very much the correct answer. It is saying all those x for which fx is equal to 1 is singleton 1. Which are those real numbers to which f is assigning the value 1? Here f is given by 2 to the power x. I have to find those x which are sitting in the collection of all reals for which f of x, which is 2 to the power x, is 1. This implies 2 to the power x is 2 to the power 0, because 1 is nothing but 2 to the power 0, and because, as you can see, this is a 1, 1 function, strictly increasing. take the horizontal line test. This function is going to pass the horizontal line test. And by that we know if f of x is equal to f of y, because over here we have f of x is equal to f of 0 implies x is equal to 0 since f is one-to-one function. And therefore you have the only x to which fx assigns the value 1, or the only x for which fx is equal to 1 is x equals 0, and therefore set of all those x such that fx is 1 is the singleton set 0, and therefore the answer is not equal to singleton 1 but singleton 0, and therefore B is wrong. Going to C, it is saying, does f satisfy that f of x plus y is equals to fx into fy? Let's verify that. So, f of x plus y is nothing but 2 to the power x plus y, which I know by exponential rule is 2 to the power x into 2 to the power y. But this is nothing but fx into fy. This is true for all xy coming from R, and that is why it is true that f of x plus y is equals to fx into fy. The D says none of these are true. Well, it is false because yes, 2 of the options among the given 4 are definitely true. I have just used the concept of exponential function for a greater than 1 to solve this. After that, it was really very nice sailing process to come to the end of this question and get our solutions marked among the options. Let's now proceed to understand what question number 9 has to say to us. Question number 9 deals with the relations concept. It is saying that the relation R defined on the set A. When I am saying on set A, the first thing that should come to my mind is that this R is a subset of A cross A, such that this relation is given by all those ordered pairs are going to sit inside R such that the modulus of the difference of their squares is less than 16. Whichever ordered pair satisfies this, it is going to get an entry inside R. I have to verify whether or not which of the options are true. True on which basis? It is saying is not given by. That means if this is not equal to my relation R, then I will mark this as my correct answer. If this is not equal to my relation R, then I will also mark this as the correct answer. If this C is not equal to my relation R, then also I will mark this as the correct answer. That is what the question is trying to say to us. So let's see which of the following relations given in point number A, B and C do not satisfy this relation R. So let me name this as R1, let me name this as R2 and let me name this as R3. I have to show R1 is actually consisting of ordered pairs which satisfy this rule or not. That is what I have to show. So R1 given to me is consisting of 1, 1, 2, 1, 3, 1, 4, 1 and 2, 3. Does this satisfy the rule of the relation or not? Let's see. Well, x, y belongs to R only when the modulus of the difference of their squares is less than 16. Consider this. Does this satisfy the rule? Well, modulus of difference of their squares. This is nothing but 0, which is definitely less than 16. If you pick up this you get modulus of 2 square minus 1 square, which is nothing but 1, definitely less than 16. It's not 1, it's 4 minus 1, that is 3, which is again less than 16. If I move to the third ordered pair, I get modulus of 3 square minus 1 square, which is 8, less than 16. If I move to this, what is it that I get? I get 16 minus 1, giving me 15, which is less than 16. If I pick up this, I get 2 square, which is 4, minus 3 square, which is 9. What is it, the answer? 5, which is strictly less than 16. And so R1 definitely is a relation given by this rule. That means R1 does come by satisfying this rule, and therefore this A cannot be the correct answer. Moving to R2, if you carefully observe R2, what is R2 given to you? R2 has 2, 2, 3, 2, 4, 2 and 2, 4. That is what is given in R2. Does all the ordered pairs sitting inside R2 follow the rule or not? Well, if you look at this ordered pair, 2 square minus 2 square is 0, which is strictly less than 16. If you take modulus of 9 minus 4, you get 5, which is strictly less than 16. If you take 16 minus 4, you get 12, which is strictly less than 16. And if you get 4 minus 16, again modulus of that brings you 12 in picture, which is again less than 16. So even R2 is coming just like R1 from this given rule, and so R2 also cannot be the correct answer. Because the correct answer is that relation which is not given by this rule. Let us see if R3, the left out relation, is following this rule or not. Well, let's check here itself. 3, 3, that means modulus of 3 square minus 3 square, which is 0, which is strictly less than 16. No problem with this ordered pair. 4, 3, modulus of 16 minus 9, which is what? 7, right? 7 is strictly less than 16. This is what? 25 minus 16, that modulus again less than 16. 9 minus 16, again less than 16 if you take the modulus. That means R3 is also formed by satisfying this rule. And so among all these relations, 3 relations, none of them are formed by not following this rule. And so the answer is none of these. None of the above relations are formed without satisfying this rule. That is what should have been the correct answer also. The correct answer is that option which is giving a relation not given by this rule. But because all relations are given by this rule, none of these is the correct answer. We just used our concept of relations, understood what the rule was trying to say, applied it and got the answer. Let's see what is there coming up to us in the very last question of this section. Question number 10 says again something about the domain of a function. Mind it, over here log is being concerned and sine inverse is also concerned. As I told you, the sine inverse function has its domain equal to -1, 1 and the range equal to codomain is -pi by 2, pi by 2. That means for sine inverse x to belong to reals, or for sine inverse x to belong to -pi by 2, pi by 2, x should come from the valid domain for sine inverse, which is -1, 1. and therefore for sine inverse to act upon something, this something should come from the domain of sine inverse. So this implies log to the base 2 x square by 2, this should come from minus 1, 1, which implies log x square by 2 to the base 2 should be greater than equal to minus 1 and less than equal to 1. Why don't we try and draw the graph of log x to the base a where a is greater than 1. The graph is this for that particular log, which is log x to the base a where a is greater than 1. At 1, it is 0. And I know that log x to the base a is equal to y if and only if a to the power y is x. So if I am saying that my log is between minus 1 and 1, that means this is what I am trying to say. My log values is between minus 1, 1 means here only when the domain points are from where to where is what I have to see. Well, they will be from here to what? To here, this portion. So what is this portion? For my log x to be from minus 1 to 1, my x should be from here to here. That means I want that particular x for which log x is minus 1. For which x to the base 2 is log x equal to minus 1? Well, log x equals minus 1 if and only if 2 to the power minus 1 is x, which implies x is half. And therefore, I have that log of half to the base 2 is minus 1, and therefore this arrow is nothing but half. And here I want my such x such that log x is what? 1. That means for log x to be equal to 1, this is possible only when 2 to the power 1 is x by the definition of log, which means x is equal to 2, implying that log 2 to the base 2 is what is 1. So whenever x is lying between half and 2, log x is lying between minus 1 and 1. That means log of x square by 2 is lying between minus 1 and 1, provided x square by 2 is lying between half and 2, which implies 1 is less than equal to x square is less than equal to 4. Now if I make you understand the graph of x square, well, between minus 2 and 2, I have which kind of a graph? Well, at minus 2 it obtains the value 4, at 2 also it obtains the value 4, at minus 1 and at 1 it obtains the value 1. I want those x's for which x square is between 1 and 4. These. This is possible only when x is satisfying what? Well, if x is between minus 2 and minus 1 and x is between 1 and 2, only in that case x square will be from 1 to 4. Because if x falls greater than minus 1, then x square will be less than 1. That is what and scenario if you study, you will find that whenever x is greater than equal to minus 2, less than equal to minus 1 and x is greater than equal to 1, less than equal to 2, only for these values of x, x square is between 1 and 4. And therefore you get the answer is from -2 to -1 closed interval union 1 to 2 closed interval. It is for these values of x's for which this expression falls inside -1, 1, which is the domain of sine inverse, and only then can sine inverse act upon it to deliver real values as answers, and that is why the valid inputs happen to be these values of x's, which is -2, -1 closed interval union 1, 2, making A, B, D as the wrong answers and only C as the correct answer. This is the end of the discussion about the questions related to the advanced level in the chapter Relations and Functions. We will be proceeding with something else in next lecture. Till then, study well, revise these concepts and practice these questions. Thank you.